Welcome! In this session, we'll be tackling the problem titled Non-Negative Integers Without Consecutive Ones. This is a fascinating problem that combines binary representation and constraints on sequences. Stick around as we explore the solution approaches step by step. The goal of this problem is to determine how many non-negative integers, up to a given number n, do not have consecutive ones in their binary representation. To clarify, we are working with numbers from 0 to n inclusively, and for each number, we will examine its binary form. If any two adjacent digits in the binary representation are both ones, that number is excluded. The input will be a single integer n, which specifies the upper bound of our range. The output is an integer representing the count of all valid numbers within this range that meet the criteria. For example, if n is 5, we are tasked with counting all valid numbers less than or equal to 5 that do not have consecutive ones in their binary form. The result in this case would be 5 because there are exactly 5 such numbers, as we will explore shortly. To understand this further, let's break down the binary representations of all numbers from 0 to 5. The binary forms are as follows: 0 is 0, 1 is 1, 2 is 10, 3 is 11, 4 is 100, and 5 is 101. Among these, the number 3 has a binary representation of 11, which contains consecutive ones, so it is excluded from our count. The remaining numbers, 0, 1, 2, 4, and 5, do not have consecutive ones and are therefore valid. This gives us a total of 5 valid numbers. Similarly, for another example, if n is 10, we would follow the same process to find the valid numbers in the range. Now let's look at the case where n is 10. The binary representations of numbers from 0 to 10 are: 0 is 0, 1 is 1, 2 is 10, 3 is 11, 4 is 100, 5 is 101, 6 is 110, 7 is 111, 8 is 1000, 9 is 1001, and 10 is 1010. Out of these, we exclude all numbers with consecutive ones. Specifically, 3, 11, 6, 110, and 7, 111, are invalid because they contain consecutive ones. This leaves us with the valid numbers 0, 1, 2, 4, 5, 8, 9, and 10. Counting these, we find that there are 8 valid numbers in total. For smaller values like n equals 1, the process is similar, but there are fewer numbers to evaluate. When n is 1, we are only considering the binary representations of numbers 0 and 1. The binary form of 0 is 0, and the binary form of 1 is 1. Neither of these numbers has consecutive ones, so both are valid. This means that the total count of valid numbers is 2. The problem also specifies certain constraints and edge cases to keep in mind. For instance, the smallest input, n equals 1, is straightforward since there are only 2 numbers to check. On the other hand, for the largest input, n equals 10⁻9, we need to ensure that the solution is efficient and can handle such a large range. Additionally, there are specific cases such as when n is a power of 2, like n equals 8, where the binary representation contains leading zeros beyond the most significant bit. In such scenarios, the solution must correctly account for these leading zeros. For n equals 0, the only number in the range is 0, which is valid, resulting in a count of 1. A key insight for solving this problem is that it boils down to efficiently counting numbers without consecutive ones in their binary form. Given the constraints, a direct approach that checks each number individually would be computationally expensive, especially for large values of n. Therefore, the solution needs to leverage techniques like dynamic programming or bitwise manipulation to optimize the computation and ensure it runs efficiently, even for the largest inputs. To solve this problem, we first considered a brute force approach. The intuition here is straightforward: iterate through all integers from 0 to n, convert each number to its binary representation, and check if it contains consecutive ones. If it doesn't, we count it as a valid number. The steps are simple: loop through each integer, convert it to binary, check for consecutive ones, and increment the count if it's valid. Finally, return the total count of valid numbers. However, the complexity of this method makes it impractical for large values of n. The time complexity is n log n, because converting a number to binary and checking for consecutive ones takes log n for each number. The space complexity is log n, due to the storage required for the binary representation. While this approach is easy to implement, it's inefficient, especially when n can go up to 10 to the power of 9. This trade-off between simplicity and performance is why we need a better solution for larger inputs. To address the inefficiencies of the brute force approach, we turn to dynamic programming. The key insight here is that the structure of binary numbers without consecutive ones follows a Fibonacci-like pattern. By leveraging this, we can count the valid numbers more efficiently. First, let's break it down conceptually. For a given bit position, whether you can place a 1 depends on the previous bit. This constraint allows us to define a recurrence relationship. Specifically, we observe that f(i), the count of valid numbers with I bits, can be calculated as f(i1) plus f(i2). This is because if the current bit is 0, it can follow any valid combination, but if it's 1, the previous bit must be 0. The steps involve initializing a DP array to store the count of valid numbers for each bit length, starting with f(1) equals 2 and f(2) equals 3. We then compute the values iteratively using the recurrence. To find the count of valid numbers up to n, we convert n to binary and use these pre-computed values to traverse the binary digits, ensuring no consecutive ones are allowed. This method avoids the inefficiencies of iterating through all numbers, making it far more suitable for large inputs. The dynamic programming approach offers significant improvements in efficiency. Its time complexity is O log en, because we only compute Fibonacci values up to the number of bits in n and traverse its binary representation once. The space complexity is also O log n, as we store only the DP values needed for the computation. Compared to the brute force approach, this is a dramatic improvement, especially for large n. The trade-offs here include the need for a more careful implementation to ensure accurate binary traversal and adherence to the recurrence relationship. However, the benefits far outweigh these challenges. By directly computing the result based on the binary structure of n, we avoid the exponential growth and complexity that comes with processing each number individually. This makes the DP approach much faster and more scalable. In comparing the two strategies, we see that the dynamic programming approach is optimal for this problem. It avoids the inefficiencies of brute force by leveraging the Fibonacci-like properties of binary numbers without consecutive ones. The brute force method, while conceptually simpler, is not feasible for large values of n due to its high time complexity. The key insight, or the aha moment, came from recognizing that the constraints of the problem align with a Fibonacci recurrence. This allowed us to break the problem into smaller, manageable subproblems and compute the result efficiently. The final time complexity of O log n and space complexity of O log n make this approach both elegant and performant. By balancing simplicity with efficiency, this strategy is the best choice for solving the problem within the given constraints. To begin, the problem we are solving involves finding all integers between 0 and n that do not have consecutive ones in their binary representation. The brute force approach to solve this problem is straightforward. First, we iterate through all numbers from 0 to n using a simple loop. For each number, we convert it into its binary representation using Python's built-in bin function, stripping off the 0b prefix to focus solely on the binary digits. For instance, if the number is 5, the binary representation becomes 101. Next, we check if the binary string contains consecutive ones by searching for the substring 11. If we find it, we discard the number as it doesn't meet the criteria. This approach systematically evaluates each number to determine validity based on the problem's constraints. After identifying valid numbers, we keep track of them using a counter called valid_count, which starts at 0. For each binary string that does not contain the substring 11, we increment this counter. This process continues until all numbers up to n have been evaluated. Once the iteration is complete, the value of valid_count represents the total count of valid numbers, and this is the result we return. However, while the brute force method is simple to understand, it can become inefficient for large values of n. To address this, we can use an optimized dynamic programming approach. Instead of checking each number directly, we focus on counting valid binary strings by their structural properties. Specifically, we define dp I0 to represent the count of valid binary strings of length I that end in 0, and dp I1 to represent those ending in 1. This structured approach avoids redundant computations and leverages the properties of binary strings to improve efficiency. Now, let's define the recurrence relations that form the foundation of the dynamic programming solution. To construct a valid binary string of length I ending in 0, we can append a 0 to any valid binary string of length I1, regardless of how it ends. This gives us the relation dp I0 equals dp I1 0 plus dp I1 1. On the other hand, to construct a valid binary string of length I ending in 1, we can only append a 1 to a valid binary string of length I1 that ends in 0, ensuring we avoid consecutive ones. This gives us dp I1 equals dp I1 0. For the base cases, a binary string of length 1 can either be 0 or 1, so dp 1 0 and dp 1 1 both equal 1. Using these relations, we iteratively fill the dp table for lengths from 2 up to the number of bits in n. Additionally, since we only care about numbers less than or equal to n, we impose constraints dynamically by traversing the binary digits of n and carefully applying the rules to include or exclude certain ranges. Let's explore the key insights from our approaches. The brute force method is intuitive but inefficient for large values of n because it requires iterating over all numbers and checking each one for consecutive ones. This leads to a time complexity of n*k, where k is the average number of bits in the binary representation of numbers up to n. In contrast, the dynamic programming approach focuses on constructing valid binary strings directly, which eliminates the need to explicitly generate and check every number. This significantly reduces redundant computations and makes the approach more efficient, with a time complexity of k, where k is the number of bits in n. Another important optimization comes from understanding the constraints imposed by n's binary representation. By pruning invalid ranges early, we can further reduce unnecessary computations and ensure only valid numbers are considered. The dynamic programming solution relies on specific data structures to achieve its efficiency. First, we use a 2D array called dp to store counts of valid binary strings ending in 0 or 1 for different lengths. This array has dimensions dp, k, 2, where k is the number of bits in n. Another key component is the binary representation of n itself, which helps dynamically constrain the range of numbers we consider. Addressing edge cases is also critical. For example, when n is 0, the result is simply 1 because the only valid number is 0. For n equal to 1, the result is 2, corresponding to 0 and 1. For larger n values, especially those with many bits, the algorithm's efficiency is maintained through pruning and constraint handling. Special cases, like when n has leading consecutive ones, require careful attention to ensure that the constraints are respected throughout the computation. Finally, let's analyze the complexity of both approaches. The brute force solution has a time complexity of n*k, where n is the upper limit and k is the average number of bits in the binary representation of numbers up to n. It uses constant space, so its space complexity is 1. On the other hand, the dynamic programming approach is much more efficient, with a time complexity of k, where k is the number of bits in n. The space complexity of this approach is also k, because we use a dp table to store intermediate results for binary strings of different lengths. This optimized approach ensures scalability even for large input sizes, making it a significant improvement over the brute force method. The given Python implementation solves the problem of finding non-negative integers less than or equal to n that do not contain consecutive ones in their binary representation. Here's a step-by-step explanation of the solution. 1. Fibonacci precomputation. A key insight for this problem is that the count of valid binary numbers of length k without consecutive ones follows the Fibonacci sequence. The code starts by precomputing the Fibonacci numbers for integers up to 30 bits, since the maximum number is 2 to the power of 31 1. This avoids recalculating them repeatedly during the main logic. 2. Binary representation processing. The algorithm then iterates over the binary representation of n from the most significant bit down to the least significant bit. This is done using a loop where k starts at 30 and decrements to 0. 3. Bit checking. For each bit position k, the code checks if that bit is set in n using the bitwise in operation, n and 1k. If the bit is set, the Fibonacci number corresponding to k is added to the result. This accounts for all numbers smaller than n that have a 0 in the kth position and are valid up to that point. 4. Consecutive ones handling. If two consecutive ones are found during the traversal, the function immediately returns the current result. This is because any numbers greater than this point would not be valid. 5. Final adjustment. After processing all bits, the algorithm adds 1 to the result to include n itself if it does not contain consecutive ones. The algorithm efficiently avoids generating all numbers up to n, leveraging the properties of Fibonacci numbers and bitwise operations to achieve a time complexity of O(1) constant time, due to the fixed number of bits, 31. This makes the solution highly efficient even for the largest inputs. Here, we start by creating a class called solution and implementing the method findIntegers, which takes an integer n as input. The first step is to precompute Fibonacci numbers up to 30 bits. This is because the Fibonacci sequence will help us determine the count of valid numbers without consecutive ones for each bit length. We initialize an array fib of size 31, setting the first two values to 1 and 2, as these represent the base cases. Then, using a loop from 2 to 30, we calculate each subsequent Fibonacci number as the sum of the two preceding values. Once the Fibonacci numbers are pre-computed, we move to processing the binary representation of the input number n. To do this, we initialize a variable preb bit to track if the previous bit was set, another variable result to store the count of valid numbers, and set k to 30, which corresponds to the most significant bit in a 31-bit representation. As we iterate through the bits of n, starting from the most significant bit, we use a bitwise AND operation to check if the kth bit is set. If it is, we add the corresponding Fibonacci value to the result. However, if the previous bit was also set, indicating consecutive ones, we immediately return the result since numbers with consecutive ones are not valid. Once the loop finishes processing all the bits of n, we return result plus 1 to include the number n itself, provided it does not contain consecutive ones. This adjustment ensures that n is counted as a valid number if it meets the criteria. Finally, we include a main method to demonstrate how the solution works. Here, we create an instance of the solution class and define an example input n is 5. When we call the findIntegers method with this input, it calculates and outputs the result. This example allows us to test the implementation and verify that it correctly identifies non-negative integers without consecutive ones up to the given input. To solve this problem, we start by pre-computing Fibonacci numbers, which will help us efficiently calculate the count of valid integers later. The Fibonacci sequence is defined such that each number is the sum of the two preceding numbers. We initialize fib 0 equals 1 and fib 1 equals 2 because the smallest numbers without consecutive ones are 1-bit and 2-bit values, respectively. Then, for each I from 2 to 30, we calculate fib I equals fib I1 plus fib I2. This gives us the Fibonacci sequence up to 30 bits, for instance, fib equals 1, 2, 3, 5, 8. Now, we process the binary representation of the given number, n equals 5, which is 101. We initialize preb_bit to 0, result to 0, and k to 30, as we will analyze the binary digits starting from the most significant bit. With the binary representation of n equals 5 as 101, we begin iterating through its bits. When k equals 2, we check if the second bit is set to 1. Since it is, we add fib 2 equals 3 to the result, making result equals 3. Because the previous bit was not set, preb_bit equals 0, we update preb_bit to 1. Next, for k equals 1, the first bit is 0, so we reset preb_bit to 0 to indicate no consecutive ones. Finally, for k equals 0, we see that the 0th bit is 1. We add fib 0 equals 1 to the result, resulting in result equals 4. Again, since preb_bit equals 0, we set preb_bit to 1 to reflect the current bit. After processing all bits, we perform a final check and add 1 to the result to include n itself, as it is valid. This gives us a final result of 5. Now we analyze a new example where n equals 10. We begin by pre-computing the Fibonacci numbers as before, resulting in fib equals 1, 2, 3, 5, 8. The binary representation of n equals 10 is 10, 10. We initialize preb_bit to 0, result to 0, and k to 30, preparing to process the bits of n from the most significant to the least significant. For k equals 3, the third bit is set to 1, so we add fib 3 equals 5 to the result, making result equals 5. Since preb_bit equals 0, we set preb_bit to 1. Next, for k equals 2, the second bit is 0, so we reset preb_bit to 0. For k equals 1, the first bit is 1, so we add fib 1 equals 2 to the result, giving result equals 7. Again, because prev_bit equals 0, we set it to 1. Finally, for k equals 0, the 0th bit is 0, so we reset prev_bit to 0 again. After processing all the bits of n equals 10, we perform a final check. Since we've included all valid numbers less than n, we add 1 to the result to account for n itself, as it satisfies the condition of having no consecutive ones. This gives us a final result of 8. Next, let's consider another example with n equals 18. Once again, we pre-compute the Fibonacci numbers, resulting in fib equals 1, 2, 3, 5, 8. The binary representation of n equals 18 is 10010. We initialize prev_bit to 0, result to 0, and k to 30, setting up to analyze each bit of n starting from the most significant. For n equals 18, we begin analyzing the bits. When k equals 4, the fourth bit is set to 1, so we add fib for equals 8 to the result, making result equals 8. Since prev_bit equals 0, we set it to 1. For k equals 3, the third bit is 0, so we reset prev_bit to 0. For k equals 2, the second bit is also 0, so prev_bit remains 0. Next, for k equals 1, the first bit is 1, so we add fib 1 equals 2 to the result, resulting in result equals 10. As prev_bit equals 0, we set it to 1. Finally, for k equals 0, the 0th bit is 0, so we reset prev_bit to 0. With all bits processed, we add 1 to the result to include n itself, as it satisfies the conditions. This gives us a final result of 11. The time complexity of this algorithm can be broken down into two main steps. First, we pre-compute the Fibonacci numbers. This involves generating a Fibonacci sequence up to 31 elements, corresponding to the maximum 30 bits of an integer. Since each Fibonacci number is calculated using the sum of the previous two numbers, and there are only 31 iterations, this step is constant in time and takes 31, which simplifies to 1, because 31 is a fixed, constant value. Next, the algorithm processes the binary representation of n, starting from the most significant bit and working down to the least significant one. For each bit, a constant amount of work is performed, such as checking if the bit is set using a bitwise operation, accessing the pre-computed Fibonacci number, and performing a few basic assignments and comparisons. Since there are at most 31 bits, this step also takes 31, which simplifies to 1. Combining these two steps, the overall time complexity is 1, as all operations depend on a fixed input size of 31 bits, regardless of the value of n. Now, let's analyze the space complexity. The algorithm allocates an array of size 31 to store the pre-computed Fibonacci sequence. This requires 31 space, but since the size of the array is fixed and constant, this simplifies to 1. Additionally, the algorithm uses a small, constant amount of auxiliary space for variables such as prev_bit, result, and k. These variables do not depend on the size of the input, so their contribution to the space complexity is also 1. When we combine these, the total space complexity remains 1, as no part of the algorithm scales with the size of n. This efficiency in space usage is a key advantage of the approach. Comparing this optimized method to a naive approach highlights its efficiency. A naive method would involve generating all non-negative integers up to n and checking each one to see if it contains consecutive ones. This would require examining the binary representation of each number, leading to a time complexity of n asterisk log n, where log en accounts for the number of bits in each number. For large values of n, this quickly becomes computationally expensive. In contrast, the optimized approach uses pre-computed Fibonacci numbers to calculate the result directly, without generating or evaluating all numbers. This reduces both time and space complexity to 1, making it far more efficient, especially for large inputs. Additionally, the best, worst, and average cases for the optimized algorithm all run in 1 time. This consistency is due to the fact that the algorithm processes a fixed number of bits and performs the same operations regardless of the specific value of n. Finally, let's solidify the understanding of these complexities with a mathematical proof. The algorithm's time complexity remains constant because it processes exactly 31 bits, performing a fixed number of operations for each bit. This means the time required doesn't change regardless of the value of n, making it 1. Similarly, the space complexity is constant because the Fibonacci array has a fixed size of 31 elements, and no additional memory is allocated based on the input size. Since both time and space complexity are independent of n, the algorithm is highly efficient and well-suited for problems involving large input values. Here, we'll explore some common mistakes to watch out for when solving this problem. First, one frequent issue is incorrectly handling the binary representation of numbers. For example, if you use str, bin int x, without slicing off the 0b prefix, the resulting string can cause logical errors during comparisons. Always ensure your binary strings are properly formatted. Next, brute force implementations can be highly inefficient. Iterating through all numbers up to n and checking each one individually might work for small inputs, but for large n, the time complexity of n*k, where k is the binary length, becomes prohibitive. Using dynamic programming or bit manipulation is a much more efficient approach. Another common issue is off-by-one errors, such as misunderstanding that the range is inclusive, from 0 to n. This can lead to overcounting or undercounting, especially in edge cases like n equals 0 or n equals 1. Finally, small inputs like n equals 1 or n equals 2 are often overlooked in testing. These cases are crucial because they can expose weaknesses in how minimal inputs are handled, which might lead to broader failures in the algorithm. Another critical mistake involves misunderstanding the concept of consecutive ones. For instance, some might confuse overlapping consecutive ones with non-overlapping ones, resulting in false negatives. A number like 101 might be incorrectly flagged as invalid if the definition of consecutive isn't properly applied. Now, from an interview perspective, this problem provides a great opportunity to showcase pattern recognition skills. Understanding binary patterns, using techniques like sliding windows, bit masking, or even prefix sums, can lead to more advanced solutions. It's also important to identify optimal subproblems. Consider whether solving for smaller binary prefixes helps in solving for longer prefixes. Dynamic programming and bit manipulation are both valuable approaches here. While dynamic programming is easier to explain and implement, interviewers often appreciate the additional efficiency and lower-level understanding demonstrated by bit manipulation. Lastly, always be prepared to discuss edge cases. For example, how does your algorithm handle n equals 0, powers of 2, or numbers with all ones in binary, like n equals 7 or 111? These discussions can set you apart as a thoughtful and thorough problem solver. This problem also connects to several related problems that can help you build your understanding. For example, LeetCode 191, number of 1 bits, introduces binary manipulation basics, which are foundational for this challenge. LeetCode 338, counting bits, dives deeper into efficiently counting set bits across a range of numbers, which can inform your approach here. Naturally, LeetCode 600 itself is directly related and often considered an advanced variation of these concepts. Additionally, LeetCode 70, climbing stairs, might seem unrelated at first, but it shares similarities in recursive and dynamic programming techniques. Now, when it comes to alternative approaches, dynamic programming is a popular choice. A top-down method involves using a recursive function with memoization to solve smaller binary prefixes and build up to the full problem. This approach is easier to understand but might have higher overhead due to recursion. On the other hand, a bottom-up dynamic programming approach computes solutions iteratively, starting from the smallest binary lengths and working up to log 2, n. While more efficient, this method requires careful initialization and iteration. Beyond dynamic programming, bit manipulation is another highly efficient approach. By using bitwise operations, you can directly determine whether a number contains consecutive ones. This method is extremely fast, but it can be harder to implement correctly and even harder to debug if something goes wrong. Another interesting strategy is a greedy approach combined with backtracking. Here, you start with the most significant bit of n and recursively count valid numbers. This method strikes a balance between efficiency and correctness, but it can be a bit tricky to generalize to other problems. Each of these approaches has its own strengths and trade-offs, so it's important to choose the one that best fits the problem requirements and your familiarity with the techniques. By understanding these variations and refining your implementation, you'll be well prepared for both this problem and similar challenges you might encounter in interviews or competitive programming. Great work! To summarize, we tackled the problem of generating integers without consecutive ones, explored a dynamic programming solution, and discussed its efficiency. Remember, mastering problems like this sharpens your binary manipulation and algorithmic thinking skills. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!